In this video, we're going to go over part 2 of the solutions for the worksheet of week 10. So number 7 says, find the first three non-zero term of the Maclaurin series for f of x equals e to the minus x squared cosine of x. So first and then we need both of those series. So the series for cosine of x is a series from n equals 0 to infinity of minus 1 to the n, x to the 2n over 2n factorial. And so if we check some of the first terms of this series, we're going to have when n equals 0, we have 1. When n is equals 1, we have x squared over 2. And then we're going to continue to have more terms. But for now, I'm just going to use 2 terms. Since likely, if I only need 3 non-zero terms, if I use 2 from this series and 2 from this series, we multiply, that's going to give me more than enough. Now, the series for e to the x is, of course, for n equals 0 of x to the n over n factorial. And so, if I do e to the minus x squared, this is just a composition with x squared here. So this is n equals 0 to infinity minus 1 to the n, x to the 2n over n factorial. And so given this series, this is going to give me a couple of initial terms. I'm going to have one of the first term, x squared over 1 factorial is going to be my first term here, and then plus, and it's going to continue going here. So if I just doing e to minus x squared cosine of x, I'm just doing the multiplication of these 2 series. So it's going to be 1 minus x squared over 1 factorial plus whatever, and then 1 minus x squared over 2 plus whatever this is. And so at the end, the first couple terms can come out from the multiplication of these terms and these terms. This is going to be 1 minus x squared over 2 minus x squared, and then this to multiply is going to be plus x to the 4 divided by 2. So the first 3 terms is going to be 1 minus 3 half x squared and x to the 4 over 2. Those are the first 3 non-zero terms in the Maclaurin series for the multiplication series of e to minus x squared cosine of x. Now for number 8, we want to find the interval and radius of convergency of f of x equals n factorial 2x minus 1 power to the n over 4n. Notice that this series can be rewritten, so it's actually around a certain point. So I can see this as n factorial x minus 1 half to the n, and because I have a 2 to the n over here that I can pull out of this, and I have a 4 over n here, then I can simplify that, and I can simplify this series to be the series from n equals 0 to infinity of n factorial over 2 to the n x minus 1 half power to the n. Notice that 4 to the n is 2 to the 2 to the n, or 2 times 2 to the n, and so I can see that as 2 to the n times 2 to the n, and I can cancel one of the 2 to the n's, and so that's why this is what is going to be left. Now, of course, to find the radius of interval of convergency of this, the most easy thing that I can do is do the ratio test. So I can do limit of the absolute value of an plus 1 over an, and this is just going to be a limit when n goes to infinity of n plus 1 factorial over 2 to the n plus 1 over n factorial 2 to the n, and this is the limit when n goes to infinity of n plus 1 factorial 2 to the n 2 to the n plus 1 n factorial. And so at the end, this is just limit when n goes to infinity of n plus 1 over 2, which is going to give me infinity. And so now the radius, this what that implies for the radius is that the radius is 0. So this means that it only converges at the point x equals 1/2, or when we have the 0 series. Otherwise, this is going to be a divergent series. Now, on number 9, we suppose that we have a function with the property that f of n of 4 is minus 1 to the n over n factorial over 3 to the n over n plus 1. Now, notice that in general, this is just saying that the 4 coefficient, which is f, or not really the n coefficient, but the 4 coefficient, but the n coefficient, the an coefficient is f of n of 4 over n factorial. And this 4 is only the point that we're using in particular for center in our series. So if I find an by using this, I'm just divided by n factorial, and this is just minus 1 to the n over 3 to the n plus 1. And this is the coefficient of the Taylor series. So now if I just want to find out what I want to find out that the approximation with the fit polynomial to f of phi can be with an error less than 0.2, I can use some information from here. So first thing, notice that this is the coefficient of an alternating series. So if I want to calculate the error to 5, let's say f of 5, so with the, let's say, t of the fit polynomial at x. In general, this is like for any x, not necessarily for 5, but in particular for 5, this is going to be less or equals than r of 5, right? Which is this is the error between the difference between the polynomial approximation and the function. But now, because this is an alternating series, this is going to be less than b of 5 plus 1, so b of 6. Okay? And it turns out that I can find out who the sixth term is. Well, I should say instead of, or b of 6, but remember that b is just a term without the alternating piece. So we can see an as minus 1 to the n bn, right? And so what this means is that 1 over 3 to the n over n plus 1 is what b is. And so that means that this is just 1 3 to the 6 times 7. And turns out that with that coefficient, this is approximately 0.002. So this is saying, yeah, the error for this approximation is actually less than 0.02. And we just need the information here on the coefficient to make that calculation. Now for number 10, we want to approximate sine of x to the 4 accurate to 4 decimal places. So essentially, and then again, because sine of x is the series from n equals 0 to infinity of minus 1 to the n x to the 2n plus 1 over 2n plus 1 factorial. This is another alternating series, and later when we're looking for the error, notice that this is something that we're also going to go for the n plus 1 term of this sequence, and we want that to be less than, I don't know, 0.00. So a number, we want 4 decimal places. So we want to be less than number 10 to the minus 5. So 0.0005 here. Now, because sine of x is this, then if I compose and I do sine of x to the 4, this is just going to be the series from n equals 0 to infinity of minus 1 to the n. And then composing this with x to the 4, this is going to be x to the 8n plus 4 over 2n plus 1 factorial. And now I integrate between 0 and 1. That's going to be the integral from n equals 0 minus 1 to the n. And so I'm going to integrate this piece over here. And so I'm going to have x to the an plus 5 over an plus 5. Okay? And so now I'm going to put this between 0 and 1. Of course, notice that when n is equals 0 at the start, the minimum power that we're going to have is x to the 5. So that means that we're plugging in 0, all that power in 0 is going to disappear. And where we're plugging in 1, everything is just becoming 1. So this is just the series from n equals 0 to infinity of minus 1 to the n, 2n plus 1 factorial, times an plus 5. Now I want to know how many terms of this I'm going to actually need for this. So if I go with the first term, I'm plugging in 0. So I'm going to have 1 factorial here. So this is just going to be, oh, and by the way, I forgot. Yeah, I forgot this is like 1 here to the an plus 5. It is 1, but just so you know that that's what I did in there. Now, if I plug in 0, notice that this becomes 1 and this becomes 5. So this is just going to be 1 over 5. Which, by the way, in decimal terms, that's 0.2. And in the next one, when n is equals 1, then this is going to be 3 factorial down here, which is 6. So this is going to be 1 over 6. And this is going to be 1 over 13 over here. And if I compute what this is, then this is 0.001228. You can, of course, use calculator here for this. When n is equals 2, this is plus 1 over 5 factorial, 1 over 21. And so at this point, I'm getting 0.0004. So notice that I'm getting very close to my target. The next one's probably going to be smaller. And so my approximation is just going to be given by this. But let's make sure that the next one is smaller. So for the next term will be minus 1 over 7 factorial times 1 over 29. Now this 1 over 29 times 7 factorial will be giving me a term 0.000068. So that's much more smaller than 0.00005. And so because of that, with this term we have enough error. So we're just going to approximate up to this point. Okay, so we approximate to R3. With R4, the errors with B4 is going to be smaller than this. And so this is going to be a good approximation. So now if I add this with my calculator, this is going to give me 0.1876. So this will be my approximation accurate to 4 decimal places. Last but not least, then we have use the Maclaurin series for the log of 1 plus x to approximate 1.4 log of 1.4 to 2 decimal places. So same thing as before, log of 1 plus x can be seen as the integral of 1 over 1 plus x, which I can see as the integral of the alternating geometric series, or this is just the series for an n equals 0 to infinity of minus 1 to the n x to the n plus 1 over n plus 1. This is my series for log of 1 plus x. Notice that this is an alternating series, so again, I'm using that the error is less than the n plus 1 term. And now I want that the n plus 1 term is up to 2 decimal places. So it should be less than a number 10 to the minus 3, so less than 0. Let's say 0.005 for my appreciation. Now, if I'm doing log of 1.4, this is like doing log of 1 plus 0.4. And so really, this is the series when n equals 0 to infinity, and plugging here 0.4. And so now we start looking by that approximation term. So now with n equals 0, I'm going to get 0.4 here. So this is my term B0. With n equals 1, I get 0.4 power square, and this is my term B1, and this is of course divided by 2. And with 3.3 to the 3 divided by 3. And if you look at power, what these powers are going to be, this is going to be 0.4. This is going to be 0.08. So you can have a good idea of when more or less things are going to stop. This is going to be 0.010. So now you get there. And then the fourth term, I'm going to have 0.4 power to the 4 over 4. And now this is going to give me 0.0064. Now this is getting into the range of the right decimals that I want, but this is 64, so this is larger than what I want. So likely my approximation is given by this, and the next term is going to confirm that. The next term is going to be below this number, and so that's what's going to confirm that I should just use this for my approximation. And so now the next term is 0.4 power to the 5 divided by 5. And of course, if you use this in the calculator, this is just going to be 0.002 approximately. And of course, that's less than 0.005. So this is a very good approximation to 2 decimal places. And you add these numbers, and this is going to give you your approximation. This is a minus here. Okay, so this will give you the approximation to log of 1.4 to 2 decimal places. Okay, so this is the end of the solutions for week 10.